Yes, welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal, of the people of the Aurora Nation, and I'd like to pay my respects to elders past, present, and future. So I'm thrilled to have Gerard Tripp with us today. So Gerard is a consultant economic geologist, specializing in the field applications of structural geography, geology and stratigraphy applied to exploration and the development of gold and copper resources globally. So with 30 years experience in mineral exploration for a range of mineral deposit styles on several continents, he provides high demand practical tools to assist geologists in exploration and mining environments, including geological mapping and advanced structural geology from region to mine and drill core scales. And he is going to give us the lowdown today on our exploration toolkit, and it is going to be an awesome session. I hope you all enjoy it. Please use the chat. We'll be opening up the floor for some fun and discussions at the end. And yes, thank you so much, Gerard, for joining. I'm really grateful to have you here. Okay, good.
So this presentation is really, I'll just set a little timer on the side here that'll keep me from wandering off. I'll make it 45. Right, go. So this is really not a very highly technical presentation. This is more about the kind of thing that I give to a lot of the groups that I consult to, very much associated with mining and exploration teams that are working on ore deposits, and it's very much practically and industry based, and effectively just the main communication that I try to get through with this is that there is a whole bunch of tools and techniques that we need to have in exploration, and I'll just go to slide number 1. And so there's a whole range of these things that people need that are physical skills that they can use with their eyes, with their hand lens, with their camera, with their hammer. That are skills that everybody needs to have, and there's a whole range of them, and we don't need to be an expert in any one field. I think that's one of the themes in economic geology. Very much, we don't need to be an absolute expert in structural geology or geochemistry or geophysics. Those specialists are available to help us, but when we work for mining companies and exploration groups, really what we are focused on is the search for mineralisation and alteration. And so those range of things are what I'm going to go through. And as I said, it's not super highly technical, but I've got a few little tricks and things to show you that are pretty fun to have in the field. But we're talking about really basic stuff: mineral and rock recognition, how to recognise minerals and rocks, how to do geological mapping. So many people that I go and see now actually don't know how to do basic geological mapping, and so it's one of those skills that we want to make sure that people have when they're working in the search for mineralisation, for sure. So we need some tools to recognise and particularly recognise different alteration and mineralisation styles. We need some structural geology. Everybody who works in ore deposits must have at least some skills in structural geology, and again, it doesn't have to be at the expert level, because you've got a whole range of people you can bring in. And so geophysics, lithogeochemistry, exactly the same thing. We need to have a fundamental level of ability in those fields, enough to get us through, enough to allow us to ask the questions that can be answered by specialists. And then, of course, everything has to go into 3D. So again, exploration techniques, we need a working knowledge at a modest practical level. So I'll just run through these various things right now, and hopefully I'm going to be able to do that. Okay, so mineral and rock recognition. So when there's 5,000 mineral species known to mankind. We don't need to know all of those, but there is a whole group on this little list here that it is very useful to have at least some familiarity with, and that includes the rock forming minerals, the sulfides, the carbonates, the ferrosilicates, and so forth. And it's not a huge list, but it's a list of minerals that we will come up against again and again when we're working in mineralized environments. And all you need to do is a set of sharp eyes, a hand lens, some hardness testers. I just emptied my vest on the side there. That's all the stuff I carry around with me. Primarily because, and people ask me, why do you carry all that junk around with you? And it's because when I get out there, I want to be able to do some tests on the rocks that I'm looking at and be able to answer some questions. And if you can't get to the answer you need, then there's a bunch of other things we need to do. So we go to a little mineral book, or we get a PXRF, or we use a petrologist. That's effectively what we want to do. So there's a couple of little tricks. Here's one that we use quite a lot in exploration, particularly with drilling, because we're this is the chips on the side there. That's from an RC hole. So what we've done is taken a perfectly good rock and smashed it into tiny little bits of chips like that, and that can be quite challenging to then be able to recognize minerals. And so we use these polishing plates so that we can remove all of that scratching and broken surface and get down to what we need to see. So here's a couple of chips that you would get out from an RC hole. They look pretty similar, and just visually, you wouldn't really call them those things differently. But if you polish them up, what we get on the left is a fine-grained mudstone, and then on the right-hand side, you can see there's a texture in that rock. That's an igneous rock texture, and even though the color is not typical of a mafic rock, this is actually a mafic high magnesium basalt. And so those two chips that look pretty similar like that, when you polish them up, they couldn't be more different in terms of their composition and how you would interpret them and put them on your map. And as I say, particularly in weathered environments in the eastern goldfields and the Archean generally, unless you're in Canada, of course, the Archean in Western Australia is pretty challenging. And rock recognition can be tough. Even if you're experienced, it can be difficult. And, add on top of that alteration, metamorphism, deformation, weathering, and you end up with something that's actually quite difficult to recognize in the field. So we use a lithogeochemistry, we use a PXRF, use a petrologist. The main point is that we don't just leave this as an unknown. I don't know what the rock is. It was that rock with the spots, that's not going to quite get us there when we want to put our geological map together, which at the end of the day is the most important tool of exploration. So you can see, you can plot just PXRFs are really good now for things like titanium and zirconium. So my look at all this weathered rubbish in the chip trays on the left, photograph on the left. If I zap that, I've got titanium at 8,000 ppm, zirconium at 47. I can plot them up on my little graph and work out that I'm in the mafic field, mafic or ultramafic rocks. And so if you can't do that, then you just keep pushing and pushing until you can find out what that rock is. And that's really the way we want to do it, so that we've got a really good geological map. Okay, so geological mapping is the next pretty important skill that we need to have, and it's all about the scope of what we're trying to achieve. Are we trying to do detailed prospect scale mapping or regional reconnaissance? In exploration, we're primarily attempting to define a drill target, and so what we're doing is economic geology mapping, and that means we're mapping alteration and mineralisation particularly, and of course we need to know the geology as well. But the scales, look, the scales are quite what we would call large scales, 5 to 1,000, not the regional type work that's done by the geological surveys. And so depending on what we're trying to do, so we want to map a stratigraphic section, we're mapping a mine face, a river outcrop, underground backs, all of those scales and requirements require a different approach to what we're trying to do. And so these days, you can, if you're a crusty and old guy like me and you're still using a notebook, that's fine. But these days, most of the mapping that's getting done by the professionals is on tablets, on mobile phones, and there's all those apps that we can download. The apps are really quite good, very accurate, and all the rest of it. And you're getting immediate digital capture. And I've certainly used the tablets up for mapping in places, like in some pretty wet places, and they're waterproof, and you can go out and get all your mapping down. It's all collected. The the data is immediately digital, and you've got your GIS layers, your geophysics, your drill hole database. It's just the whole thing is there right on the spot as you're trying to determine what's going on with a particular outcrop, and that's a great thing. Okay, so however you do it, whatever the capture method, still there's a few requirements, and we need to know the distribution of outcrop. That's really important. So the shapes of the outcrops need to be recorded. So you do it on a Jeep, so walk around the outcrop with the GPS if it's not, the bush isn't too thick. You can record it on a tablet, trace it on a photo overlay on your tablet like that, or you can do it on a mapping board. Some people still do. But once you've done that, then you've got to traverse the outcrop, because so this outcrop in the middle here, I don't know if you can see my mouse moving around on the screen. You can. So that little outcrop through there. So there's the edge of the outcrop. That's good. Now I know the shape of it. So I'll start to walk across it, and I find that the rock type changes across the outcrop. So now I've got a purple thing over here. That's an ultramafic rock. The green stuff in the middle, that's a mafic rock. And then there's a big fault through here, and then everything's felsic on the side. So there's some sedimentary rocks on the left. So the outcrop suddenly has some structure. Once I find those contacts, I'll walk along the contacts to try and trace them out to see if they're folded or if they're planar. And then there's some little drill collars and things. So I've got a couple of structural measurements of foliation. There's a fault through here. I've got its orientation, big quartz vein, that kind of thing. So that outcrop, that's good, that's done. And so for the rest of my map area, I'm doing the same kind of thing here. I'm putting down facing where I can find it, younging information, stratigraphy, bedding, tips and strikes. So this is the kind of mapping where when we get a final interpretation, we're going to be able to read the map, which is quite important. And all those little collars through there, all the little dots, those are just basically fresh rock determinations of what the rock type was. So you get every piece of information you can in the mapping area. And now that data set, we'll just flick between those. That's the one before. And now here's the interpretation of that area. And you can see there's a significant amount of extra information that's come into that, but I've got a whole series of different compositional units, and but there's a lot of other information on there, like faults and even some features. This hatchet feature down the middle of the ultramafic unit through here, that's purely from geophysics. So when I've got my fact data layer, I then bring in all these other layers like the geophysics. This particular project had a lot of really high quality 4-acid digest lithogeochemistry and soil data, and so we were able to, for areas where there was no surface information, you could look at the chrome numbers. They're over 3,000 ppm. Okay, that's going to be an ultramafic rock. So we're using all of those data sets to try and make the map as good as we possibly can. Okay, so when we're doing this kind of mapping, the two most important questions, because we work for industry, or certainly most of the work I do is for industry, the two most important questions are the rocks altered and are the rocks mineralized, and that's really where we're going with this kind of mapping, because it's that's the real big push for us is discovery and finding new resources, and so that's really what it's all about. So when we go out to do that mapping, we need to act like prospectors as well, which means we want to be able to recognize sulfides, oxides and sulfates, and be able to recognize things like sulfide rusting that tell us about the presence of former sulfides in the rock. And that's important because nearly every mineralization type has sulfur associated with it, you know, so that no matter what kind of ore deposit model we're talking about, that's usually what goes with it. And so these become really quite important. So there's a very basic kind of method that I teach to people every year. There's no rocket science here. It's really basic stuff. But what we want to have is, as well as mapping out the distribution of those outcrop shapes and the different rock types, just a little bit more detailed information at certain points on the mapping area. And so things like location, what's the lithology, is it altered, is it mineralized, what structure can I recognize, looking at oxides, and that's weathering, of course, but it also includes evidence of boxwork, the evidence of former sulfides. Do I see sulfates, that kind of thing in the rock? And then a bunch of other things. And so really all this is about is just having I guess a systematic way of dealing with mapping for economic geology. And the reason I kind of push this is because I'm a structural guy by training, and if I come up to an outcrop that's full of folded rocks, I get real excited and I map the folds, and I work out a whole chronology of things and write that down, and then I get back to the office and I go to the boss, hey, look at this, look at these great folds, and he's going, oh, that's great. Did you see any mineralization? It's like, oh gosh, I forgot to look. And so having this kind of method just gets you to be systematic. And if you collect this kind of information at an outcrop, you don't have to go back. So the other thing that you get from this is then a systematic data set that can be turned into a spreadsheet, and then that can be plotted to then start to spatially assess what you've recorded in your mapping. And so for each of these, you can, if you just ask these questions at each outcrop, you can be as detailed or as simplified as you like. It doesn't matter, as long as you've asked the question, got an assessment of what you think the rock is, or is it altered, is it mineralized, and so forth. And as I say, that can get as detailed as you want, or be as simplified as you want. So here's an example of a mapping project up in the Andes, and really what we were looking for was advanced argillic lithocaps, and you can see, so there's the outcrop shapes, that's all good, but all these dots are now my more detailed information that includes rock type, alteration, sulfide species and percent, vein volume percent, because it's a porphyry environment, what structures we can measure, and then the oxides. So hematite, jarosite and goethite, that's going to give us an indication of what kind of sulfides we had, the degrees of leaching, if we're in the lithocap environment, things like that. And so, so the dots at the top left here, that's all lithology. The purple things are silica caps. And then alteration, so all the green, there's epidite all over the place up in that area, in the andesites, but lots and lots of the big silica lithocaps. So now I can now take my little data set and plot up, I'm just going to move this for a sec, and plot up, whoops, an area like this. Now I can say to the client, look, this is the place where there's this really, really extensive lithocap developed from our little dots here, and that's going to give us a better idea of targeting and where we want to go for our exploration drill. Okay, so so number 3, alteration and mineralization. We want to know the model type that we're working in, and what I mean by that is that if we're working in porphyry, we don't, for instance, if we're just taking these 2 examples down the bottom, porphyry and greenstone alteration, you don't expect a lot of carbonate alteration in high temperature porphyry settings. It's just like you don't expect vertical, potassic phyllic advanced argillic alteration in greenstone environments, and that's all part of what the ore deposit models. It helps to know what you're working in, a VMS environment, I mean porphyry, I mean greenstone, that kind of thing, and then you can try to understand those or have that bit of knowledge in the area you're working in anyway. When I was at one of the previous slides, I just mentioned it's good to know, good to be able to recognize the sulfate minerals, and these are minerals that indicate the presence of former sulfides. So you may not see any sulfide in the rock at all, like the photograph at the top on the right-hand side. That's all that yellow stuff is jarosite. You can see there's a beautiful vein stockwork in through there, but there's not a scrap of sulfide. All that's left is jarosite, which is a iron, potassium, iron sulfur sulfate, beg your pardon, and that's what you get left over once you weather feldspar. In the weathering environment, you produce an acid fluid and it eats the feldspar and leaves behind jarosite. Scorodite is another. It's arsenic-rich variety, and this general kind of sulfide rusting is something that we don't want to walk past when we're in the field, because our focus is economic geology. That's really the stuff we want to. If you're walking up a creek you see all these rusty boulders coming out of one of the tributaries, that's the one you're going to go up. You don't follow the green stuff. You know, that's kind of where that goes. Okay, so in a couple of tricks for alteration, so in greenstone environments or other areas where you've got a lot of carbonate, you can use this technique of staining to tell you what the species of carbonates are. And it's a mixture of these chemicals here: potassium ferricyanide, alizarin red, and dilute HCl. And with just put a drop of this stuff onto the mineral, and it'll give you a bunch of colors that we can read off through here and work out where we're at. Now, why that would be important, because go back to this slide, there's the typical greenstone alteration diagram. So the ore is over here on the red, and so this is proximal and distal on the left. And so we're at sericite, anchorite, and pyrite, chlorite, anchorite, sericite, and then chlorite, calcite, and tremolite, clinozoisite out in the distal. And so you can map out where you get calcite, where you get ferroin calcite, ferroin dolomite, and so forth. And I'll just show you some examples of that. So this is what the staining looks like. So these rocks, the rock on the top right here, you can see the rock is clearly altered. It's a mafic rock, so it shouldn't be that pale grey color. It should be a really dark green. But so we can see that it's altered. And when I stain it up, it all comes up blue. This is anchorite, so it's covered in anchorite alteration. And so basically, this is what the sun does. If you leave this tray at the bottom here, that's a tray of drill core that was on the top and was left out in the sun for a while, and those carbonates will go brown anyway. And so what we're doing is speeding up the process when we've got brand new fresh core that comes out of the ground. So here's an example on the top left. All the grey carbonate. There was this spotty high-grade gold in it. Didn't really know why. So you can see the pink color in through here, that's calcite. The pale blue, pale turquoisey kind of color, it's not quite turquoise, but it's pale blue, that's ferroin dolomite. And the really dark color through here, see these little fractures cutting through here with high-grade gold, that's ferroin calcite. And so there's actually multiple phases of carbonate alteration superimposed, but it's one stage that's got all the really high-grade gold with it. And that's useful information to have. If you're in places where you've got manganese carbonates, rhodochrosite, so all that white stuff in through there, I would never recognize that as manganese carbonate, but it stains brown. And so that tells me that I'm dealing with rhodochrosite. Okay, so mineral percentage estimates is another really essential tool for the economic geologist. If you're working in copper, it's essential. You can't get away with it because unlike gold, copper is fantastic. If there's copper in the rock, you're going to see it, and you're going to be able to estimate the grade based on how much copper that you can see in the rock. And so we want to look at the disseminated proportion, the vein proportion, and then work out an estimated grade. And so the Anaconda guys came up with a really good method, and they did this. I think it was in the Yarrington pit, because they couldn't keep up. The production guys couldn't keep up with the labs couldn't keep up with the production, and so they needed a way to estimate and say this is going to be ore, this is going to be low grade, this is going to be waste, and they were able to do this visually to probably about 5 or 10%. So it's pretty good when you can do it. The graph on the right is what we normally get in all of our books, and it's for chunks and phenocrysts and clasts. It's less applicable for sulfides. Sulfides normally deport as these tiny little dots in your handlands, and so a graph that gets you from 0.1 to 1% is generally more useful for that kind of thing. And so, given that you're looking in the handlands at a volume percent, we then need to convert that to a weight percent copper. So in the sulfide is chalcopyrite. I've got 1% volume percent in the handlands. That's going to equate to 0.47% copper in the sample weight percent. So you can use charts like this and come up with quite an accurate estimate of what your copper grade is. Another little field trick you can do when you're working in copper terrains. If you ever see these black coatings, if we were in say a place like Kalgoorlie, there's this black stuff on fractures all over the place. You don't worry about it because it's just manganese oxide. But when you're in a copper terrain, it's not just MnO2, it's quite often tenorite or neodysite, and these are copper-bearing oxides, and we can take a piece of that, you put some dilute HCl in it and scratch bare steel on it, and it chins native copper onto the bare steel. And that's when you're working in those kinds of areas. Anytime you see black coatings like that, you've got to do the field copper test, and that's a pretty fun thing to do, and really useful for your mapping. Okay, so structural geology is one of the other key skills that we need as economic geologists, because structural control on ore is the norm. It's what happens in nearly all ore deposit types, and I always emphasise this to people because a lot of people find structural geology a bit challenging and a bit scary, to be honest. And as soon as you roll out stereo nets, they get really scared and they run away. And I think, but if you're going to be working in ore deposits, there must be a basic working knowledge of structural geology as it relates to ore deposits. So we don't need to be an expert. You don't need to be able to unravel polyphase deformation. If you do, then you can get somebody in to help with that. But being able to recognise some basic stuff like bedding and way up, like tell the difference between a fault and a shear zone, recognise folding and veins, of course. That's really, really important. And then this little point here, measure it, plot it. I'll talk about that when I get to a slide that's coming up, and show you a couple of other tricks that we can use. So when we're doing structural geology, stratigraphy is where we start. We must know the sequence, we must know the way up, and if we can't, then there's a certain equivocation that hangs around our interpretation. So if we say, yeah, I've got a thrust terrain, but I can't tell you what the sequence was, or I can't demonstrate the facing of the sequence, then, well, maybe it is thrusting, maybe it's something else. It's always just leaves a bit of uncertainty. So if we start with, we get the rock sequence and the way up, that gives us the architecture, then we can map out the fabric catalogue that comes after. So those are the first things. And then everything comes out. You can start counting fabrics and faults and shear zones that come 1, 2, 3, 4 after that. But that's really the important thing. So this little diagram on the right, sorry about that, is a little map of Kalgoorlie. It's when you just look at the geology map, the color geology map of Kalgoorlie. It's quite a lot of colors, and the structure doesn't jump out at you really. But when you just take a little bit of facing here, so that's the purple unit and the green unit. That's older, the green one's younger, and we've got an old map here from a guy called Keats in 1987. He's got pillow facing, all sorts of facing indicators. Now we can put that together and say, right, now I can see the structure. I've got a refolded early fault band fold that is actually maps out the major structure of the area that's got 60 million ounces of gold sitting on this early D1 fault that's been refolded around an F2 fold. So that's really important stuff, and we get that from something as basic as just which way the pillows go. So there's only 3 main structural controls on ore, and I'm happy to be corrected on that, but I think they're the ones that matter the most in kind of economic environments. And certainly the most important initial control is lithological. It's related to the architecture and the structure of the host sequence that the mineralisation is imposed upon. And so what we're talking about is factors that facilitate precipitation of metals, right? And that can be those can be any of these methods: fluid wall rock reaction, fluid mixing, things that induce temperature and pressure changes, loss of confining pressure and faults, that kind of thing. And where those faults intersect, units in the original lithological sequence generally has a very marked control on where ore wants to go. So here's an example of andesitic sequence on the right here. There's a fine-grained andesitic tuff and a coarse-grained andesitic tuff, and quite clearly the coarse-grained tuff accepted alteration more readily, and embrittled the rock, and this is where the ore veins went. So it's in the coarse grain unit, not the fine grain unit, where most of the ore is. The bottom photograph is from Mount Charlotte mine in Kalgoorlie, and that's the unit 8 of the Golden Mile Dolerite. That's a 10 layered seal with 10 units, and one of those units has got a much more favourable chemical and rheological nature, and fractures more readily than all of the other units, and that's where a lot of the ore in the Golden Mile wants to be. There's a little photograph up here. This is from the Tanami, where there's a layered sandstone sequence with these little titanium-rich sand layers, and you can see a vein cuts through that, and the gold is being precipitated right where it intersects these titanium-rich layers. So there's a chemical reaction so the ore-bearing structure cuts through a layered sequence, and it's the chemical nature of the layering in the primary host sequence that determines where most of the high grade wants to drop out. So that's pretty important. And then the lower figure is from Broken Hill, where there's a layered stratigraphy, more oxidized, more reduced strata that are more and less favorable for the precipitation of ore. So really, yeah, so favorable host rocks will give you permeability, chemical reactivity, or rheologic changes that influence where ore wants to go. The rock contacts are always a really important structural control. Sedimentary rocks, differentiated layered intrusions, oxidized or reduced strata. And other places like, say, Porgera up in the PNG highlands, where you've got crystalline intrusions that cut through sedimentary rocks. You know, the ore veins come through the sediments at the side. They're only like that wide. When they hit the crystalline intrusion, they blow out to these beautiful big low sulfidation epithermal veins. The second one is the really obvious one, faults and shear zones are generally the channelways through which we get ore bodies developed, and that can be in the synvolcanic environment. So so VMS on the seafloor through here. The synvolcanic fault is the primary pathway. So the heat source is dragging down hypersaline fluids, stripping metals out of the sequence, and focusing them back up the synvolcanic faults with synvolcanic intrusions and precipitating massive sulfides at the seafloor. Typical orogenic style shear zones and veins in through here. This is from Junction, a nice breccia zone with a sigmoidal shear vein array. That's generally what a lot of these things look like in the orogenic environment. And down the bottom here, beg your pardon, down the bottom, the Larder Cadillac break, you can see that there's probably 120 million ounces of gold on this diagram, and there's certain changes in the orientation, certain little complications in the shear zone is where these camps are turning up with major gold deposits. So faults and shear zones, that's everybody knows that. I know I'm not saying anything mad here. And of course, the last one is folds. Fold culminations, focused fluid flow. Everybody knows that. Red Lake isoclinal fold on an ultramafic contact is where most of the super high grade is focused. Everybody knows about the old Bendigo saddle reef style of ore deposit, where you're getting extension in the hinge with flexural slip folding, and the ore bodies form right on the stacked saddle reefs that go, look at that, 1,400 meters all the way down. And another example would be the Zambian copper belt. So this is Shambishi. That's the lower Rowan carbonates in through there. And the ore shales are, I mean, there's a whole bunch of things happening in Zambia, but the ore shale is the first reductant. And so these hypersaline copper-rich fluids move upward through the sequence, and they hit the first reductant, and most of the copper drops out. But it's not ore. It's anomalous nearly everywhere, but it's not ore everywhere. And it's where we get later deformation that focuses that sort of lower grade halo into fold culminations. And so an example down through here, the copper is mostly remobilized into low mean stress sites, and this is what changes background anomalism into ore bodies in the copper belt. Okay. And of course, another thing that economic geologists, particularly mine geologists, want to focus on is ore chutes. And this is really important because if you've got a planar or a tabular body of ore, it is very rare to have a uniform distribution of grade over that tabular area. And there's nearly always some sort of linear control related to, say, fault hinges or a stretching lineation. This is pyrite. In this particular deposit, the pyrite is gold bearing. And so this is actually giving us the orientation of high grade within the deposit. And you can just put your compass on that and measure it, and immediately you've got some very important information about that. Shear zones and splays, intersecting shear zones, produce these linear bodies of preferentially fractured rock and linear chutes that are generally plunging it down into the ground. Okay. So with ore chutes, there's another old trick that was invented by this guy, H.J.C. Connolly, back in Norseman, 1936. And we can still use this. Of course, we do it in 3D these days in Leapfrog, but it's a really good technique, and it's related to, deriving a structural control on high-grade ore from an analysis of the topography of the ore surface. And so really, you can see the vein in cross-section through here is not right in the center of the diagram, is not, it's not planar, it's got rolls and bends, and it's, and what Connolly noticed was that where these rolls and bends happen, if he could map them out, he could actually, and compare them to grade, he could derive structural controls on the ore. And I'll just show you a really good model example of that. So this is the Bullion Hulu vein. So just take note of the scale down at the bottom. That's 1,000 kilometers, sorry, 1,000 meters on the scale bar at the bottom through there. So we're talking about 2 by 2 kind of kilometers or more, 3 by 2 kilometers. And so really all we're doing here is looking at this. This is not grade. This is distance to the ore surface. And so this is a cross section on the left. By creating a reference plane and then measuring the distance to the vein, we can then color that up by distance and make a set of contours that now tell us what the shape of the vein surface is, right? So just think of this diagram on the right now as like a map. We're looking down onto a topographic surface, and the hot colors are closer to me and the cool colors are further away. And so you can see that we've got a hill over through here. The contours have suddenly broken across a fault here. There's a fault. This is the Bullion Hulu fault that just pops straight out because the contours are broken across that fault. And so this is a hill, and then we kind of go down in this direction, sort of down to a bit of a valley. Then we come up again a little bit and then drop right off into another valley like that. And so that's really telling us what the shape of the vein surface is. And that's great. So we don't know anything about grade yet, but now we can compare that to things like grade thickness, vein thickness, and then see what comes out of it. And so there's our Connolly diagram on the top left, and now here's the distribution of grade, gold grade. And it's really hard for me to see, but that's quite a high gold range. I think it's like 50 grams per ton. So let's just have a look at that. So the one on the left and the gold, well, the hill or the topographic parts that are closer to me are not the areas that have got the highest gold grade. And then if you have a look at the diagram at the bottom, the lode thickness. So this is thickness in, I can't read that either, thickness in meters. So again, the thickest part of the lode is not the area associated with the highest gold grade. It's actually a narrower part of the lode where the highest grade is, and it's forming a chute that's plunging very steeply down to the right through here. Then as we come up again a little bit, the grade drops off, and then as we go back down into the valley, down here the grade picks up again. So there's a relationship there. And it doesn't really mean, I mean, there is something in the background here, which I'll tell you that in a sec. But when you do this kind of analysis, it's different for every ore body, and you've just got to plot it up and have a look and see. Just look at what the relationships are, and you'll get the answers here. And so the thing to note about Bullion Hulu is that the ore is boudinaged. And so, so now I'm not surprised by this at all. There is a strong post-mineral boudinage on the ore veins, and that's really effectively what we're seeing here. So the thickest parts of the lode are not necessarily higher grade. The higher grade is focused into the boudin necks, where we're probably getting preferential fluid flow or even remobilization of the ore. So that's a really cool trick to do as well. Okay, rightio. So structural geology and drill core. We want to be at least conversant with that. A lot of people are doing this now. Most people are. I think in terrains where you get nice, good core coming out of the ground, there's a lot of places around the world that don't even bother, because if you're in a tectonically active environment, the core falls to bits. A lot of porphyry environments, core just falls apart as soon as it comes out of the ground, so they don't even bother. But when you do this, and you can actually get some really good data and use it. Core protractors are generally the method that people are using these days. It's okay, it's good. It's good if you want lots and lots of data, but as explorationists and as mine geologists trying to find ore extensions, we want probably better quality and more thought out measurements, rather than just lots and lots of thousands of readings of something. Well, that has a limited usefulness for structural interpretation anyway. The core frame is a really good one, because we can measure it with a compass. We get everything we want straight away, and most importantly, as we're moving down the drill hole and logging the core, we're actually getting a 3D picture in our heads of the structure, and the picture is building up as you're going down the hole, as opposed to taking alpha beta type readings, take them back to the database. That might get in by next week or in the afternoon, whatever. Then the next day you've got to try and think back to what you were doing and understand those orientations. So certainly for the kind of work I do anyway, this is my preferred method of dealing with structure and drill core. Measure it, plot it. So the other thing to do is, when you're on the core, you plot the data straight away, because structural geology is one of the few disciplines where you can immediately use the data. Like if you're a petrographer, you've got to take a sample. Well, it's got to be made into a thin section. It's got to be looked at and analysed, and a report written. And by the time you get it back, you're a month or two out from when you first collected the sample. And the immediacy of what you wanted to know about that is kind of a little worn off. Geochemistry is the same thing, and of course we've got to do it. But when you're taking structural readings and making observations, it's right there on the spot. This is when it's happening. And so if we're taking that data, making those observations and putting them down and starting our interpretation straight away, it really it's a much better way to deal with your data, rather than just to collect a whole bunch of it and then come back and look at it much later. Okay. People must always be aware of drill core quality control. Structural data is drilling is a very biased data set. It's just a line going into a very complicated 3D geometrical natural occurrence. So what we should see in the data is not this. These stereo nets here are showing unnatural distributions, a very strong rotation of the veins around the drilling core axis, the axis of drilling. We should never see the measurement method. Natural data don't care which way you look at them or which way you measure them. Those populations should have a natural distribution, and this is what would be a very typical unnatural distribution. So this is very important to check when you're dealing with drill core. Okay, so number 5, geophysics. I've got 2 minutes left and 2 more subjects. We need a working knowledge of geophysical techniques and ore response. Again, don't need to be an expert. And so that means that if you're working in sort of greenstone orogenic veins, porphyry environments, VMS, just for an example of a few, then there are certain features that are going to be, IP chargeability, EM conductivity, and so forth, resistivity, just understanding what factors in each of those model types affect or are affected by what the geophysical responses are. And again, as an economic geologist, somebody working for a company, you don't need to be an expert, but you need to understand that, you know, like certain sulfides going to need a certain conductivity, and they're going to light up in EM or IP, that kind of thing. Okay. So I think the other key issue is this statement here that an anomaly is something that's unexpected. So if you've got a mag high, it's not an anomaly until it's telling you something you weren't expecting. So for instance, I've got a map at the top here where we've got in the little dash box, there's a pink unit here, that's a granite. All the colored units on the left here, they're greenstones. And so they're high magnetic, high density features. We would expect, we know they're greenstones, the aeromagnetics tells us that, the outcrop geology tells us that. We're expecting to have, I guess, big bunch of high density rocks. When we look at the gravity in the little white dash box through here, we can see that there's the texture in the background, that's the magnetics. But now we've got a big the tongue of low gravity that's just coming out underneath those high density rocks. So that's an anomaly. That's a gravity anomaly, proper one. We expected high density, we got low density, and that's the anomaly. And so those are the kinds of things we want to pick out. And you know, I don't know if you've got, so remember the old wallaby, the wallaby mag high out in the middle of sedimentary rocks, and suddenly there's this big point magnetic source. Well, that was an anomaly sticking out that had to be drilled. You know, so that's the kind of thing we're talking about through here. So these big gravity features down through here, they're not anomalous. They're sitting under big gravity highs, sitting under thick sequences of mafic and ultramafic rocks. That's entirely expected. Okay, finally, lithogeochemistry. Again, a working knowledge, and we've got really good tools like IOGAS now that help people to use their geochemical data like a lot more than when I was ever a young exploration geologist, that's for sure. We want to collect grid data, we deal with downhole data, and the main things we get from it are lithology discrimination, alteration indices, if you like, pathfinder signatures, and then there's also another chemical data set we want to use, that's shortwave infrared for white microchemistry, and that's become really, really important in a lot of places. So why do we do grid geochemistry? Because ore deposits are small, but their alteration halos are big, and so we need it to collect data in a grid to effectively map across the system, to map the fluid system. And that's really what it's about. And so this is the arsenic distribution. So there's 100 million ounces of gold in this area that I'm circling through here. This is just arsenic above detection. You can see it's just a big green cloud of high arsenic in the background there. And so that's giving us the scope of the system. So a grid is really important. And I know that sounds a little bit obvious, but sometimes people don't really understand that and collect a sample here, a sample there, and that kind of thing. But that's not really giving you the picture of the system. So in places like this place here, Mount Pleasant, the lithogeochemistry allowed us to separate one of the host basalt sequences out into 3 units, and we found that most of the really good deposits are sitting in one of those units, preferentially over the others. I mean, that's part of the power for exploration. So you map that unit out wherever you can and go and drill it. That's kind of where we're using that in exploration. So shortwave infrared data is I'm going to race through this real quick. This is a really nice example from Kanowna Belle, and this is bottom of hole. So these are all vertical drill holes, and these are the little bottom of hole samples that have been analysed with a PEMA. Well, you do it with an ASD these days, and that's okay. That doesn't really matter. But what we did see was that so Kanowna Belle ore body is here. Let's say it's I think it's 7 million ounces of gold. Last estimate I was told. It's plunges like a pencil right on this area through here. There's a structure, the Fitzroy Fault comes down through here. There's a footwall sequence, a hanging wall sequence, and right on that structure is where the 7 million ounces of gold is plunging. Now, when we look at the alteration in the rocks, we just see white mica alteration, and no, I don't. For a lot of these things, we would just call it sericite, or white mica or muscovite. But when you look at it with shortwave infrared, you can determine the compositions of the white micas. And so what we saw was in the south that there are cooler muscovite to paragonite compositions, and right on the boundary through here, we go to higher temperature phengitic white mica compositions. So now I don't really know the implications or the science behind that, but as an explorationist, I've got a tool now because I've got a gradient in mica composition, and right where that gradient falls is where the major ore body is. So I can now step out on the next slide to the camp scale. And so now here's the outline of the pit down through there at the bottom. There's my muscovite to phengite transition right on the gradient. And now here's this big cell of high temperature phengitic compositions which is fantastic. Now I've got a whole extra exploration space to go and test, just that's been mapped out by this sort of gridded white mica chemistry in through there, and a few other areas around the district where I'm seeing the same thing. So so a really, really valuable exploration tool. And you can use multi-element geochemistry for mapping. So here's a quick example from a VMS district in Turkey, up on the Black Sea coast, and the rhyolite paleosurface. There's in red, that's the little massive sulfide at Chaley. The red in through here, that's the rhyolite in the footwall, and it mapped out a whole other rhyolite paleosurface that we didn't know about at the time. So it's great. And you can even see folds in the geochemical data. So how about that? The new Scott Helley reckons that geochemistry is the new structural geology. What do you reckon about that, Richard? Anyway, finally, this is the second last slide. So everything we're doing today, these days, is integration. It's all about integration, and it's all about operating in 3D. Everybody is operating in 3D all the time, which is great, really, really good. And so there is still, I guess, there's still a need for young people that initially coming into the industry to learn how to plot on a map and to learn how to make a cross section. Absolutely, but the value of all of that geological information comes through when we get it into 3D, and we can really analyze large data sets quickly. But again, it's just a 3D program, and it's all about the quality of the data and the quality of the geological observations that go into it. I think that's important. Okay. Oh, well, sorry, this is the penultimate slide. So finally, and most importantly, I think it's really important to not just go and collect miles and miles of data. More data is good, yes, but it's got to be, and I'm just talking about structural data in this particular case here, collect enough data to answer questions and solve the problems. So space the observations out appropriate to the scale, right? That's really important. So here's two examples where these are drill holes. This is a drill hole on the left where it had about 50 or so structural readings taken, and from that you can map out the fold architecture. You've got the facing. That's all good. The diagram on the right has got about 50 million structures taken, and you can't really do a lot with it. And so that's what I mean. So there's just data overload on the right here, and it's less useful for what we're trying to do is to understand the structure and to generate a drill target. Righto. So all of those things that I just outlined are kind of the toolkit, and I'm thinking the toolkit for field geologists, really. There's a lot of other great new stuff that is coming out of research groups and and the government, like CSIRO. There's a lot of really good stuff coming up from CSIRO that we're trying to get from the research stage into the practical sort of end. But the Amira Green Rock project would be a great example of that, where a whole lot of detailed academic work was done that was then turned into a whole range of things that we can put on the PXRF to use in the field and understand the difference in epidate compositions and things. That's really, really important. So there's a range of field-based tools and advanced technology tools, and a lot of these things are now what we call standard best practice. Most of the big companies are doing this. That's great. But we're trying all the time to filter that down to the juniors. And I know it can be an issue of funding and all the rest of it. However, those things are great, but the field fundamentals are still absolutely crucial, right? So we can only sit in offices and rehash the same data over and over so many times. Sooner or later, somebody's going to have to go out and look at a rock again and come up with something new. And so therefore we need those field skills to do that. I think if there's any young people watching or who are going to listen to this, just understand that a lot of these techniques are learned through experience and on-the-job training. When you work in industry, you're not expected to pop out of industry and know all of this stuff. That's fine. And I think most of us more experienced people learnt this bit by bit as we went through. So I think that's really important. And don't worry if there's stuff in here that doesn't that you're not right on top of straight away. That's okay. It'll come. Okay, so integrating data sets is the norm. All of those things have got to come together: the mapping, geophys, lithochemistry, structural geology, and so forth. And exploration targets and new mines is what it's all about. And if I can encourage everybody to read the discovery literature, there's a fantastic literature out there. I've got all the new Gen Gold volumes right here next to me on the bookshelf, and there's a bunch of things out there that can help. Okay, Jess, I'll leave it there.